It will have some electromagnetic waves and it will have some optics. It's electromagnetic waves and optics. And we'll kind of go a little bit further into it. Okay, I hate this room. And I've been in this room a lot. All right, so first things first. I brought stuff today. So I'm gonna write a dark, I'm gonna do an H here. And I'm gonna do another H. And we talked about electromagnetic waves, and we talked about the wave nature and the particle nature of electromagnetic waves. This is a crystal, okay? This is a naturally occurring crystal, and this is something that Newton or Poisson or Heisenberg or Huygens or any of them would have. And if I put this in there over my H, it gets, let's see if I can make it. If I go one way, I get nice crisp letter, just like I would have on my sheet of paper. And if I do it another way, I get, it almost looks like, if you look at it directly, I'll have to bring it around, but it gets fuzzy and then it gets crisp. And there's another one, so you kind of get, except my optics over here are correcting it. But you'll get double, it'll fuzz up on you and it'll be nice and straight. You can get a variety of different things. So this is one of those arguments that you had wave versus particle behavior of light. Let's see if I can get this, see if this will do any better. Oh yeah, that one gives me double lines. You'll get double lines versus nice single lines. And the natural, this is a natural, what they call a polarizing crystal. So let's see if I can do these. Okay, so in this, if I look at it, oops, okay, so you can actually see through, let's see if I can get light better. Okay, so I've got light on. So you can actually see, I've got two polarizers here. And in this case, you can see through it, but if I turn it 90 degrees, you don't see through it at all. Okay? So if I got it here, now through the document camera, it's a little tougher to see, because I do get some just filtering of the light, but if I turn it 90 degrees, I get total blockage of the light. And what's happening there is we said that light was a transverse wave, but light's gonna have, if I'm looking at light, I'll have waves that go like this, I'll have waves that are kind of at an angle, I'll have waves that are up and down, but if it hits what we call the picket fence kind of definition of light, if I hit a picket fence, only the light that's oriented such that it comes through the picket fence part will come through. So I get some filtering just because I don't get the light to come through that way. But if I take one picket fence, and then, so I've got my picket fence, and then I take the next picket fence and I do it this way, if I've only filtered these, then this picket fence blocks them. And that's exactly what a polarizer is doing. That's exactly what my polarizer is doing associated with the various pieces. So we may not have to turn off the lights completely in here. See what happens. Give it a whirl. I know these will show up. So I got a block. I got my laser pointer. Let's see how that works. So, oh, that works really well. The green comes through pretty nicely. ahead and, Caitlin, can you go ahead and put the light off? Yeah, please, ma'am. All right, so we've got a nice beam that comes through. I've got my incident beam that's coming in, and I've got the refracted beam that's going through, and then of course as it hits this side, it refracts out again. I get the reflected beam up here, and then I get a reflected beam outside that refracts back outside. Now this glass, we call it smoke glass, even though our eye can't detect it, there are enough little particles in there to create scattering. And that's what we're able to see when we do the scattering, is we're able to get the pieces back and forth. And where this one's coming through is I get a refracted beam here, and this reflects back out. So I get a reflected beam that refracts back out. So that's why I'm getting multiple beams. And you can play with it depending on your angles of incidence. And then you can also get it to where I can come in and get my critical angles. So let's do a critical angle, see if I can get a critical angle on this one. Or I can come in and get it. Okay, I'm getting close, getting close. Just may not have enough. There we go. Oh, we get it. Right on the edge. I'm not getting to my spot to get my critical angle. But you can play with them, and hopefully you guys did that in lab. Then I've got a handy dandy little gizmo. My handy dandy little gizmo has got a lot of parallel beams, so we can look at things in parallel beams. So there's my square, right? So if I'm going in and I've got just my plain piece, you can see it go there. But I have some handy dandy smoke pieces that will give us so if I've got this one, this is a converging lens. And if I come in, I gotta see if I can get it. There we go, that's a nice one. I come in nice and parallel, there we go. I get a nice focus point associated with my lens. So you get the beams coming out parallel from the device. The lens gives it a nice focus point outside the lens. And when we get to thin lenses, we'll be able to actually see that, but I've got all my lenses with me today. So I've got another one, and this one's gonna have a different focal length, so I gotta play with it a little bit. See if I can get it on my piece of paper. There we go. There we go. We get a nice focus point associated with the lens. And then you can play with, let's see if I gotta put this up here a little bit, because this is not quite. So I can do mirrors. So this is a concave mirror. And we get that same, we can play with the focus point. You can see that, in this one you can see the actual aberration a little bit, because this is not a perfect mirror. But you can get those. There we go. There we go. I was missing my mirror. So that is a concave mirror, because I'm going to have making a cave. And now when we look at a convex mirror, you can see how the beams will bounce off. And the image, if I'm looking directly at it, the image will appear behind it, but you can see how the beams of light go the other direction. So we can play with the concave and convex mirror. All right, we can put the light back on. Thank you, ma'am. and we can see and play with. So optics are just cool. And a lot of your instrumentation deals with optics and how the optics play with different things. But now we're going to play, one of the things we're going to do today is we are going to do a problem associated with something that looks like this. So there is this actually is a block of optical glass. And a lot of us have played with these things, and when you go to, so if I look, there's H, right? Those H's are in the same spot in the glass, but all of a sudden it looks like it's closer to you, okay? If I have a radius, or what we call the paperweight problem, and we've all seen the paperweights, right? Paperweights with the tarantulas in them, the snakes in them, pennies in them, variety of things. They look bigger and much closer to you than what they actually, if you look at it on the side, you actually can't see it. What's really cool about these things is, I'll do one this way. So I've got this little swoosh here, okay? And if I turn it, you can sort of tell, you can actually see and could actually measure where the image is versus where the object is. Because look at where the edge of the paper is if I look at it on its side. You get a good idea, but I could take a ruler and put a ruler next to it and actually do a physical measurement with my little block. So you can play with it in terms of, I know where the image is because the image is at the bottom, or the object is at the bottom of my block. But when I look at it, and I look at it side on, I'm going to creep it up a little bit. The paper looks like it's about, in this case, looks like it's about halfway up. So you can actually take a ruler and do the measurement associated with it. See, they're fun to play with. Optics is great. And that's also why we can have glasses and we can do a variety of different things. One of the things is I did get the test graded. So the take-home tests are graded. Everything is in Blackboard now from WebAssign except what hasn't had a due date already. So the only other thing that's not in Blackboard that would affect your grade are your lab grades. You have your midterm lab grade is in there, but so if you want to know exactly where you are, I've only got one more test because we were having trouble with the file formats for the test, and I finally got it, and so I'll get that graded later. It'll probably be tomorrow before I get to it because it's Wednesday. Wednesdays is just a crazy day. But everything's in there, so you should know exactly where you stand. And then the final's only over optics. You've got 2 quizzes. You've got the quiz that's already open. That's the assessment quiz for the semester. That's the non-droppable quiz. And then there's a quiz over electromagnetism and optics so that you get up to be able to study for the test, essentially. And I think that quiz should open today or tomorrow. So you should be in good shape as far as what's left for, and I think if I didn't, no, it's not this class. I have one class that I'm actually dropping a homework assignment in. But I think I've got all your homework assignments have already been dropped or whatever associated with it. So we're in good shape from that perspective. All right, so let's kind of look at one of the things that we talked about is that we have to make sure when we're dealing with problems associated with mirrors and with objects that we have the sign conventions correct. So let's kind of just look at those sign conventions again so that you guys have a chance to remember them. And when you're making your cheat sheet for your final, this is one of the things that I would write on my final, is what these sign conventions are. So if I'm dealing with mirrors, and where we were on Fridays, we had done some of the ray diagrams in order to figure out where the mirrors would be and where the radius of curvatures are. Then we talk about the fact that on the real side or the front side where the light rays actually are, and that's why I brought in the rays so you could actually see that we're talking about where those rays are bouncing. Laser pointers and laser boxes have made it really nice to be able to look at those kinds of things. And so I've got a front side or a virtual side. The back side, remember, virtual side is if I put a piece of paper there, I'm not going to be able to see any rays of light. So just like my mirror with my laser pointer, it was going to bounce directly back out, and there was nothing really behind it. But if I'm looking at it with my eye, I actually see, or it looks like there is something behind it. And then I can have flat, concave, or convex mirrors. Now, concave, this would be the concave side. This is the convex side. So this is concave if you think of a cave. This is convex, that's the convex side. And then you've got flat mirrors. So our sign conventions are, if I'm in front on the real side, it's going to be positive. If I'm in back on the back side, it's going to be negative. If I have an upright image, it's going to be positive. If I have an inverted image, it's going to be negative. So I actually did this so that we could actually look at a problem. So I'm going to do this problem right here, that we have a 2 centimeter high object. It's placed 3 centimeters in front of a concave mirror. If the image is 5 centimeters high and virtual, what is the focal length of the mirror? So we're going to start out with a 2 centimeter high object. It's going to be placed 3 centimeters in front of the concave mirror. If the image is 5 centimeters high and virtual, what is the focal length of the mirror? What is the focal length of the mirror? Give you a second. Everybody got it? Come back to it in just a second. One of the things I want to remind us about, let's see if I have it in here. Nope, I didn't do it in here. We'll just play with the book then. Spherical mirrors. Well, no, actually, we'll go to the summary. Remember that the summary is the best part of the chapter. Right? Summaries are the best part of the chapter. The key here are the equations that we want to look at. When I have a mirror, that the focal length right here is F is equal to R divided by 2. So it could tell us, once we figure out the focal length, we can also find the radius of curvature for the mirror. So we'll add that to our problem. My object and image distance for my mirror equation is going to be 1 over P. Remember, P is where the object is. Q is where the image is. And F is the focal length of the mirror. Okay? F is the focal length of the mirror. So I'm going to write both of these down, so we'll get it here in just a second. But I want to have all my equations written down. 1 over the focal length. And then the focal length is R divided by 2. So those are going to be our 2 key equations that we're going to use. So I'm going to go back for a second. So my summary, oops, that's problem 11, just so that we got it. And this is really cool in this chapter. So when you guys are working your homework, looking at the ray diagrams, even though this is for a conceptual question, having those ray diagrams really help when you're working problems, just so that you can follow through them. So there's a nice picture in your book. And then we'll get to lenses here, probably on Wednesday. I'll focus on lenses. But we're going to problem 11. So we're doing our 2 centimeter high object, 3 centimeters in front of the concave mirror, and the image is 5 centimeters high and virtual. So what that's telling us is this. So I got my equations written. And I can see the problem again. Okay, so first thing is we want to look at our mirror. It's telling us it's a concave mirror. And if I'm drawing it and I can do this, and this is one of those times where I can actually do it with a protractor and a ruler and actually measure and do a variety of things, I'm going to end up having my R, which is my radius of curvature. I have my focal point right there, and because I don't know things, I'm going to put those pieces. We're told that I have an object that's 3 centimeters in front of this. I'm just going to put one in, and we're told, and my object was 2 centimeters high. And we're told that we get an object that is 5 centimeters, is it 5 centimeters tall? Yeah, 5 centimeters tall. So it's big and it's virtual. So virtual tells me it's going to be behind the mirror. Okay, and it's 5 centimeters high. And we are also told it's placed 3 centimeters in front. I will pick it up later, but I'm tired of picking up the pen that is dying. Tired of picking up the pen that's dying. All right, that is going to be P. That's where my object is. Okay? So I need to know where Q is. So I need to know where Q is. So I'm going to use my magnification equation. Okay? I'm going to use my magnification equation. So I'm going to get minus Q over P is going to give me my height, which was 5 centimeters, divided by my object height, which is 2 centimeters. Which gives me 2.5 centimeter, or 2.5. So minus Q is going to equal 2.5 P. We know what P is. P is 3. And that's going to give me, because I can't calculate in my head this morning, it's going to give me 7.5, or Q is going to equal negative 7.5. This negative right there tells me behind the mirror. And that's a good thing because we were told it was virtual. And that tells me that I've got a minus Q that I've got to deal with. Now, remember, we're ultimately trying to find F. That's what we're ultimately trying to find. So I've got to make sure I keep my sign convention straightened out. Now, I'm going to do something to show you because there's a lot of books that will do it this way. So I'm going to start with my equation. 1 over P plus 1 over Q is equal to 1 over F. Now, this is the equation that you'll see in our book, and sometimes you're going to see an equation that's going to look a little different, but I'm going to get you there from here. So what do we got to do? If I want to do this, because I want F on top, right? So let's do this. So if I want to do this, I want to put these into lowest common denominator, right? So if I put Q over PQ plus P over PQ is equal to 1 over F. All I did is multiply by 1 to get my lowest common denominator, which is going to be P times Q. So now I get Q plus P divided by PQ is equal to 1 over F. Now if I want just F, I flip everything over and I get F is equal to PQ Q plus P. A lot of books you'll see this equation versus that equation. Let me get that all in one screenshot. So a lot of times you'll see a study guide, or you might go to Chegg, or you might go to a tutor.com or something like this, and they'll say, well, F is equal to this. And you go, well, my book doesn't show that. Well, yeah, it does. It shows you this way. Okay? So this gets us directly there. And so just depending on how your books lay things out, you'll get this. There's also, just so you guys know, there's also another convention that's out there. Some books will do this. It'll give you 1 over O plus 1 over I is equal to F. And that's kind of nice because you remember that that's the object and that's the image, and I don't have to remember, I don't have to remember what it is. So some books will do it like this. Some books will also do it like 1 over DO plus 1 over DI is equal to 1 over F. That's also a little bit easier to remember than which one is P and which one is Q. But P and Q are standard type conventions that people use. So if I want to solve for F, I'm going to hold all this stuff up here. A little stripped up there. So let's see if I can keep my picture in, there we go. And now I've got F is equal to P, Q, Q plus P. Now I put my P in, my P was 3 centimeters, my Q is a negative 7.5, and my Q is a negative 7.5 plus 3. So now if I do this, this becomes over 4.5 and it's negative. Okay, 7.5 times 3. It gives me 22.5 and it's negative. And it gives me a positive answer, okay? Positive answer, and it gives me a positive 5 centimeters. A positive 5 centimeters. Now, if we were playing with our pictures, what that says then is this. If my focal point is 5 centimeters, I didn't bring a ruler, bummer. So I've got a concave mirror, and I'm going to eyeball it. How do I want to do this? I want 5 centimeters as my focal point, so I'm going to do that's about 2.5 centimeters, so it's about I'm using a scale of about 1 centimeter or half a centimeter to 1 centimeter. This is going to be my focal point. My radius of curvature, my focal point is my radius of curvature divided by 2, so my radius of curvature is going to equal 2 times the focal point. So this is going to be about the same distance over here. This is where my radius of curvature is for the mirror that I've got. We were told, handy dandy piece of paper. We were told that I was 3 centimeters away and my object was 2 centimeters tall. So it's going to be about 1 centimeter. So my object actually was probably right here. Okay, my object was probably right there. diagrams. So now I can come in and do an arrow across here, right? Now the arrow, this is going to reflect, but this is actually going to come back like this. Okay? I'll have a parallel, I can have my parallel and bounce off. And then I'll also have my focal point, my radius of curvature here. Which way do I want to go? Oh, my other one is like here. We'll go from there. This one's another one. Hang on. I want to make sure I've got my diagrams right. This one. Okay. That's my concave mirror, my convex mirror. Go through radius of curvature, did that one. Go through my angle through the middle, did that one. Focus. They're not giving me my pictures.
You know, I thought I found you on my stuff, and I looked at it. It was the wrong class. I'll keep looking. I promise. It has to be somewhere.
You're good.
But I know. I was like, oh yeah, I found it. And then I saw you like there. I'm like, God dang, it was not even there.
Did you get your pinhole thing done?
Yeah, that was.
You turned it in yet?
No, I just have to print it on.
All right, my other one is going to be 7.5 behind the mirror. That's 2, that's 5, 7.5 behind the mirror. Object's going to appear like that. I'll have to play with the ray diagrams. It's not jumping out at me today. But that's because the reason it's going to be virtual is because I'm inside the radius of curvature and end up the back that way. And we can play with the ray diagrams to get us there. We'll play with it. All right. So that's kind of how you approach these problems and playing with those problems as we go. The key now, though, is we want to get to lenses. We want to get to lenses. And so we start with things that aren't lenses. So we're going to do the ultimate paperweight problem. So basically what we end up with is if you look at a paperweight, I end up with a piece of glass, and usually what we do is we have some sort of radius of curvature, right? We got some sort of radius of curvature, and so that usually gives us an R associated with this. And we know, because we've done refraction and reflection, we've been playing with that, and basically the difference comes in is that this now has an index of refraction, and this is my index of refraction of error. So I get a difference between those indexes of refraction. And what ultimately happens is now I have to account for those indexes of refraction, and this ends up with the index of refraction of where my object is, plus my index of refraction where I'm looking through and where the image comes out. And then I get into minus n1 divided by the radius of curvature when I have a big object. So the paperweight problem does this. I have a flat surface, and I have a radius of curvature, so I got my radius here. And I'm gonna put a penny, a scorpion, a spider, a snakehead, all those various things that you find, shells, right? All those various things that you find in a paperweight. And this radius of curvature, so if I take it from here, this radius of curvature of my thick lens, we're gonna say has 25 centimeters. That 25 centimeters. This object in here is gonna be 2 centimeters. That's what we're putting in. The index of refraction of the glass is going to be 1.55. Air is going to be 1. And we want to find the position, and the size of the image. You want to find the position and the size of the image. We gotta watch our sign conventions. And those are important. So, if I start out with this, so I'm going to start out with my equation N1P, and this, oh, I didn't tell you this one. There's a piece of information, we place it in here at 20 centimeters. Now they can tell you in a problem that it's placed 5 centimeters away from the bottom, or they tell you it's 20 centimeters away from the top. So you've got a couple of stuff. If I tell you it's 5 centimeters from the bottom, when we plug it in, you got to know how far away it is from the top. So that's a trick, kind of a trick that they do to the problems. So you want to make sure we've got that. And then we get N2 minus N1 and my radius curvature. All right. So I put in my numbers, it's 1.55 for my glass. When I do it this way, the sign convention says that this is positive. So if I plug in things in wrong and what the sign gives me the if you got it wrong, go back and double check your sign conventions. You probably have set up the problem correctly, you just probably have missed a plus or a minus somewhere. Then I've got my air divided by what I'm looking for. Where is the image going to be? And now I've got my 1 minus 1.55 divided by, this is where my sign convention comes in as well, that's a negative 25. I'm going to sneeze.
Start the line.
It's still there.
Start naming off fruits.
Huh?
Start naming off fruits.
Start naming off fruits?
I say pineapple and won't sneeze.
I know, and no one
Yeah, you just
sneeze.
throw out random things you don't see.
Yeah. Okay, I'll have to remember that one. Well, yeah, that's the Habaduba thing. When you stub your toe, you know, as a little kid, you try to get the kid to say Habaduba, and then what's the magic word? Habaduba. And it's trying to remember it, they forget that they're hurting.
No, I was busy talking about it. Did I hear you?
Worst thing, stuffing your feet.
And there's like
So I'm going to just solve for Q here. This gives me 0.55, negative 0.55 divided by a negative 25 plus 1.55 divided by 20. If we plug that into the calculator, this gives me a 0.2 or 0.22 plus a 0.0775. So 1 over Q is equal to 0.022 plus 0.0775, and that gives me, oh, I've got a negative. I forgot a negative. That's a negative. That's a negative. That's a negative. Gives me a negative 0.0575, and then when I flip it, I get a negative 17.4 centimeters. And this negative says that it's beneath the surface. So instead of at 20 centimeters, it says I'm going to be closer to the top. And by experience, we know that, right? If I put the scorpion in there, what does it look like? It looks like it's closer to the top, right? We know that by experience. Now I got to figure out the size. And the size, I got to do my magnification. Magnification is equal to minus Q over P. My Q is minus 17.4. I still have a minus here, and my P is 20. I got that backwards? Nope. I got that backwards. It's gonna be positive, but I end up with it looking smaller, and that's not usually the case. Oh, I've got an N. Those have N's in them, I'm pretty sure. Hang on, let me flip through here real quick. Mirrors, 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 mirrors. Yeah. Yeah, I've got an N2, N1. And that ends up being like my 1.55, 17.4 divided by my 1 over 20. I knew there was something missing. 17.4 divided by 20 times 1.55 gives me 1.3485, so it's bigger. You just gotta watch your sign conventions and watch those indexes of refraction. But the whole idea behind this allows us to start doing lenses. And what happens is we go from something like this that I don't have to worry about, and remember the other piece. So when I have my lens, or have my lens, or I have my material, right? We come in with an incident angle, it's gonna refract, but when it hits this one, it refracts back, right? So I get rid of the bend as I go through my lens, or go through my glass. So what happens is we can take this glass that we've been worrying about with a radius of curvature, and we can make it really thin that I can disregard how the material is going to behave, because this path distance is very, very short. That path distance is really, really short. And so that's where it gets us to, thank you, ma'am. That gets us to a thin lens that we can play with, that we don't have to worry about this index of refraction of our material. Because what we're going to end up doing is bouncing in and bouncing out. And we'll have lenses, we'll have both convex and concave lenses, and they're going to be called converging and diverging lenses. So we end up doing things like this. I can have a lens that looks like this, and a lens that looks like this. Okay? And these are going to be what we call converging lenses, because what they're going to do as we come through, they're going to come in and have a nice focal point associated with it. The thing about converging lenses is if you look at a converging lens, which is one of the lenses that I had, right, this is a converging lens. The middle is going to be thicker than the ends. So if I pick up a lens, you know, I get a box of lenses out there, and I pick up a lens, and I get something that looks like that, I'm going to have a converging lens. The middle is going to be thicker than the ends. Diverging lenses, I'm going to come in as a, so this is going to be convex, right? I come in, and what happens when I get this, it's going to refract out. And what will happen is I come in and have this piece, I'll have lenses that look like this, and when they come out, as they come through the lens, this is going to branch out this way, this kind of will stay the same, this will branch out this way, and these are going to be diverging lenses. And they're going to be shaped, I might have, it might be a shape like this, might be shaped like this, or it might have that lovely little thin waist shape like this. But the thing about these are, they're thinner at the middle than they are at the ends. So we move from something that's thick to something that comes in to look like this, and that we can disregard this index of refraction associated with this, with the problem. And I'm going to stop there because I don't want to start lenses today. And we will tackle lenses on Friday. And we're almost done.